When a bias is applied to the p-n junction, the potential barrier height across the junction and the depletion region width are affected. As the Venn diagram represents the landscape that determines the electron and hole motion, we have to find out the new barrier height and the depletion width first. To calculate the new barrier height is relatively simple. Starting from thermal equilibrium, the barrier height is VBI. When a negative VA is applied to the p side of the junction, the Fermi level is raised by a magnitude of VA. Therefore, the new barrier height is simply equal to VBI minus VA. Since VA is negative, a minus sign has to be added to get its magnitude. In order to calculate the depletion width, we start from the charge distribution as shown here. The charge density is not affected by the reverse bias, as the charges are coming from the ionized dopants with a fixed concentration. We have to find the new XP and XN under reverse bias condition. When a reverse bias voltage is applied, charge neutrality still holds, and we can still write Na times Xp equal to Nd times Xn. Starting from the charge density, we integrate it to get the electric field. And integrating the electric field, we get the potential difference. The process is the same as what you did before to calculate the depletion width at thermal equilibrium. You will obtain the same equations of the voltage difference between the two sides of the junction, and it is equal to the expressions shown here. At thermal equilibrium, the voltage difference is given by VBI. Under reverse bias, the voltage difference becomes VBI minus VA. Therefore, you only need to replace VBI by VBI minus VA in the expressions you obtained for the thermal equilibrium case to determine the depletion width under reverse bias. That is, the depletion width of the p-n junction under reverse bias is given by the expressions shown here. Or, if you assume the depletion region is mainly contributed by the lightly doped side, it becomes the following. From the expression, you should notice that the depletion region width increases with the square root of the applied negative voltage.